I'm going to be talking about some joint work that I've done with Joel Wallman. And if you Google image search for quantum computer, the pictures just keep getting cooler and cooler every year. So ultimately we want to build some super cool device on n qubits. And in order to do that, we have to be able to characterize error rates. We have to characterize the types of errors that we have in our device. This is an absolutely essential task. Ask any experimentalist. It's essential, but it's unfortunately intractable. And so we need some sort of structural assumptions on the noise if we want to make it tractable. And so the purpose of this talk is to focus on a specific class of noisy channels, the Pauli channels. And so why should I focus on Pauli channels? That may seem a priori like a bit of a narrow focus. But this is the most relevant class for quantum error correction and fault tolerance. Those of you who attended the quantum error correction session yesterday noticed that without even thinking about it, every single speaker exactly assumed that all of their errors were independent Pauli noise. No. I guess Hector didn't quite do that. Where's Hector? Yeah, sorry, no, Hector did not. Never mind. You did. You assumed anyway. People typically assume independent Pauli errors without fail. So this is a theoretical motivation, but it's not a very good physical motivation. If you're an experimentalist, you don't care what the theorists have to say your errors should be. You care about what they actually are. But fortunately, there are tools like dynamical decoupling, which make your errors more Markovian, or Pauli frame randomization and randomized compiling, which actually enforce the Pauli projection, or they force the noise to be a Pauli channel. So I'm going to take the point of view in this talk that you've already characterized all of the coherent errors. Maybe you've used this randomized benchmarking tomography that we heard about in the last talk, or things like gate set tomography. And you've removed as much coherence as you can, and then you're going to give up. You're going to say it's too complex to learn much more about the coherent errors. I have to stop at some point, and then I'm going to randomize my channel to reduce it to a Pauli channel. So just to remind everyone, what is a Pauli channel? It's a convex combination of Pauli operators acting as Krauss operators. So the little p sub k here form a probability distribution over the 4 to the n elements over the Pauli group, modulo phase. And capital P here are just the Pauli operators on n qubits. So there's 4 to the n of them. I think I just said this. The P's I'm going to call the Pauli error rates. There's another representation of quantum channels, which is the superoperator representation, where it acts via left multiplication on a vector in the Pauli basis. And if I were to expand a Pauli channel in this basis, I would describe the Pauli channel would be diagonal in the Pauli basis, and the diagonal elements I will call the Pauli fidelities, and I'll denote them by F, okay? And so I claimed on the last slide that we can actively enforce this Pauli approximation, and we can do that by this trick called randomized compiling, which is a more clever way of doing Pauli frame randomization. And here's an experiment by Ware et al. That was done last year. This is showing the superoperator for some specific noise channel that they had in their device. When they randomize the noise using these protocols, they find that they kill all of these off-diagonal elements to within the statistical fluctuations of the statistical resolution of their experiment, and they're left with a residual Pauli noise channel, and the Pauli fidelities along this axis are left unchanged. So what that means is you really can implement this to very high accuracy. So this is, it's a theorem that you get this Pauli projection, but it's also practically true that there are no residual errors left over when you implement this. So this is, strongly motivates thinking deeply about Pauli channels. Okay, so I've argued that we need to reduce from general quantum channels. It's very inefficient to learn complete descriptions of them, and that we have some tools that will reduce the problem to characterizing Pauli channels. This is better, but it's still inefficient. I mean, you cannot learn, for example, a general probability distribution on 4 to the n outcomes, and that's the task that we have in front of us. So we need, if we want something that's efficient, we need some additional structure in the problem. So I'm going to put 2 structural assumptions on the Pauli channels. So I'm going to describe how to learn a general Pauli channel, but it will be inefficient. It'll be better than general purpose algorithms, but still not efficient in n. And then the 2 structural assumptions that I'll put on the Pauli channel are that the channel is S-sparse, or that the channel has bounded degree correlations. So by bounded degree correlations, I'm talking about a Markov random field. So it has the Markov property that if I have two subsets of qubits labeled A and B, and they're separated by some separating set C according to a graph, then the probabilities split in this way. So the conditional independence assumptions of a Markov random field. And so in this case of structured Pauli channels, we'll find that we can actually learn these things tractably. Okay, so here are the main results of this talk. For a general Pauli channel, I can learn, we present an algorithm for estimating an n-qubit Pauli channel using n times 2 to the n over epsilon squared measurements. That gives us a guarantee in the 2 norm of the probability distribution. And this I want to really highlight, it's to multiplicative accuracy, okay? So the accuracy is really important when you're talking about trying to verify error rates that are 10 to the minus 4, 10 to the minus 5, right? The record infidelities that you see, there's a trapped ion experiment where they observed error rates on single qubit gates down at 10 to the minus 6. You know, simply sampling a fair coin 10 to the 12 times rapidly runs into graduate student hours, the complexity measure that Scott mentioned in his talk. So, you know, this multiplicative accuracy is really key for applications. So then the 2 structural results are for S-sparse Pauli channels. We get something, this is modulo a conjecture. I'm glossing over a few caveats here and technical details. But modulo a conjecture, we get an S-sparse channel in time polynomial in S and polynomial in log n. And then for bounded degree Markov random fields, we can learn a Pauli channel with respect to the 1 norm now. So this is a stronger guarantee, again with multiplicative error. And this is the worst case marginal error rate. So this is how close the noise channel is locally on some particular cluster of the Markov random field. How close is that to the identity channel? And I just picked the worst one out of all possible clusters. So we get an error bound in the 1 norm on the n-qubit Pauli channel, and we get it in a polynomial number of samples, and we can deduce an efficient description of it in polynomial time in n. And I want to emphasize again, all these results are to relative precision in epsilon. So we have to make some assumptions about the noise that are physically reasonable, but it's important that we state these assumptions clearly. So it's what I call GTM noise. The noise should be gate independent. That is, when I implement a specific choice of Pauli, the noise on that Pauli is independent of which choice of Pauli it was that I chose to implement. Okay? And this assumption can be relaxed, although we don't bother to do so. But using techniques by Wallman or by Seth Merkel and co-authors, this assumption can be relaxed. We also assume that the noise is time stationary. So at each time step, the distribution from which I'm sampling remains invariant. And we also assume that it's Markovian. So we just assume that the noise can actually be described by a completely positive map. And we also make 2 technical assumptions. One, that the noise is weak in a certain sense, so that we assume that the gates aren't too noisy. And we also assume that the noise is stable, I'll call stable, which is that the measurements aren't too noisy. And this is just technically because we need some sort of positivity assumptions. I can't have those Pauli fidelities getting too close to 0 or even becoming negative, because that will ruin, I'll take a log of a negative number or some stupid thing. It's a minor caveat, and it's only, it's not a real, I don't think these are real assumptions. I think they can be relaxed, but they're real in the sense that our proof kind of requires them. You would need to have a different proof, but I don't think they're actually essential for the results. Okay, so what's the algorithm for learning an unstructured Pauli channel, a general Pauli channel? It's very simple. We do the following quantum circuit. So time moves from right to left. So we just prepare a bunch of initial states, and then we do some specific Clifford gates, C1 and C2, which I'll specify later. And in between those gates, and then we make a measurement in the standard basis. In between that, I'm going to basically power up some given channel, followed by a bunch of IID random Pauli operators in here. And this is going to average this noise in here over the Pauli group. Okay, so it's going to do a Pauli average. And M here is just the power that I'm going to choose. Okay, so I'm going to, And the goal, what I'm going to learn is the Pauli noise on these Clifford gates that I'm going to place inside the green bubble. So I'm going to do this for several values of m and for certain specific choices of C1 and C2. And then I'm going to post-process these samples that I collect at the output in a special way. And it's worth comparing to what we heard in the previous talk about randomized benchmarking. So in randomized benchmarking, I wouldn't put Pauli operators here. I would put Clifford operators here. And the gate complexity at each time step, as I tile this circuit with this unit cell, would scale like n over log n in the number of qubits. Here, it's just depth 1 every time I implement this unit cell. So this is a much more efficient circuit for characterizing noise. Another nice thing is that compared to normal randomized benchmarking, usually you have a 1-bit output at the end where you accept or reject the outcome of the measurements. Here we have much more powerful n-bit measurements, so we're able to collect a lot more information per time that we run this circuit. Okay, so if you work out the expected value of this bit string averaged over this choice of random Pauli choices here, you find that the signal that you're going to get is a sum of a bunch of different exponentials in these Pauli fidelities. And so you might think I can just take these probabilities and just fit to this ansatz to try to recover the f's, but it's a well-known problem that it's basically impossible to fit a sum of exponentials because it's a very poorly conditioned problem. It's not the kind of thing that can be solved by just taking more data. So you cannot simply fit to this ansatz to extract f. You need to be more clever. And moreover, we're actually after the Pauli error rates, and the f's are linear combinations of these Pauli error rates, so it makes the problem seemingly even more intractable. But fortunately, there's a Fourier relationship between these fidelities and then again between the fidelities in these p's. So those of you who've read a paper by Jonas Helsen and co-authors about character benchmarking, what we have is a variant of character benchmarking that allows us to effectively fit one exponential decay at a time. I mean, we can do it in parallel as well, but we never have to fit the sum of exponentials. We can isolate each one individually and fit a bunch of individual exponential decays one at a time. So that's one innovation. Fitting a single exponential decay is fairly easy. In order for us to make this useful, like I said, we need multiplicative precision. The idea behind powering up this circuit is that this is basically like the power method in linear algebra. It's what's going to allow us to get multiplicative precision in f. So we're going to keep choosing different length scales m to run this circuit at. And what's going to happen is the effective fidelity after m time steps keeps decaying, right? So one of these fidelities decays like f to the m. And so if we do this after some amount of time, which scales like the log of 1 over the spectral gap of this superoperator channel, then you can show that the ratio of the two estimates of the fidelity, which I have right here, to the power 1 over ml, this is an estimator for that specific fidelity, okay? And that's just, you just plug in the exponential decay formula to this ansatz and you can convince yourself that this is true. And if you do this, and by the way, this is where I sneak in this assumption about weak and stable noise. It's because I don't want to have to accidentally divide by 0 or take a root of a negative number here. But if I were to actually fit an exponential decay in real life, I would use something like least squares and that wouldn't be an issue. This is why this is just some sort of artifact of the proof that I need these extra assumptions, so I believe. So if you work through this argument, you find that I can point-wise estimate all of these Pauli fidelities from this experiment to multiplicative accuracy in the sense that it depends on if the channel is close to the identity channel, then I get a very good estimate of that Pauli fidelity. So I mean, maybe to make it a little more visual, the reason that we're able to do this is that every one of these experiments is done to additive precision. So if I were to fit this decay curve, though, I'm going to amplify that precision, even though every one of these estimates of these individual points is additive, the line itself is fit to a much higher precision because it's taking advantage of the fact that I know that it's an exponential slope. That's how I get multiplicative precision. I'm going to you can work this out in terms of diamond norms, and these are the answers. I'll just jump ahead. Right, so okay, sample complexity. How many measurements do we need in order to get all of these Pauli error rates? So I didn't really go into the detail about how to choose these Clifford operators. I'll mention that in a minute. So we want to get a point estimate of each of these things for a bunch of different choices of m. And for each one of these, we need some sort of additive precision. And then we're going to take some kind of union bound. And so just by a Chernoff inequality, each one of these points, I'm going to need this many samples for some fixed m. And here, d is 2 to the n. So the largest value of m that I'm going to need, I need to see some sort of contrast, right? If I go back to the slope on the previous slide, I need to have a large enough m that the initial fidelity, f to the 1, is distinct from f to the m way down over here. And so m has to be at least as large as 1 minus f, or I'll never see that, right? And I can search for that by just doubling m each time until I start to see some contrast, and then I can stop the experiment. And so that costs me some amount of time, which is like log 1 over g, where g is the spectral gap of the channel, or 1 minus f. And I can search for it in log of 1 over g time. Okay, and so the bare experiment that I described, it only gets me information about errors in one particular basis. If the Cliffords that I had chosen were just the identity on both sides, then the errors that I would be estimating would be the bit flip error rates within this circuit. But if I rotate the basis, I could learn something about, say, the phase flip error rates. And more generally, if I put any stabilizer code or stabilizer state preparation, I learn about the destabilizers with respect to that stabilizer state, right? So I can always learn about the errors that anti-commute with some code, okay? So each one of those Cs is chosen from a complete family of MUBs, and this is an optimal way to choose these Clifford operators such that I can sort of tile the entire Pauli group and learn about them as efficiently as possible. So you put all of these estimates together and you get a total sample complexity which scales like 2 to the n times log n divided by this multiplicative accuracy squared and some other factors that are sort of irrelevant. Okay, and I just want to emphasize that this is like practically, it works well practically as well. It's not purely theoretical. So these are some simulations I did on my laptop of estimating a 4-qubit channel. And I have 2 different axes here. So this is some generally correlated Pauli channel that I just sampled randomly. You can see, so the orange lines are Pauli error rates sorted by how large they are. And I'm assuming that the base error rate is something like, I forget exactly, maybe it was 10 to the minus 3 or something. So these are all of the non-trivial errors, not the identity Pauli. And you can see that the blue dots, which are my estimates, track very closely the orange dots, which are the true error rates. And for 4 qubits, this took about 200,000 samples in my simulation. If I put this on a log axis, you see that we get much better estimates of the Pauli error rates. For the larger the error rates, the better our accuracy. And it starts to trail off as we move down to lower and lower error rates. And that's sort of natural because if you have an error rate that happens 1 every 10 to the minus, or if your error rate is 10 to the minus 50, you don't expect with 200,000 samples to get a very good estimate of that. So it's natural that that the accuracy sort of degrades and that we're only getting the multiplicative accuracy at the error rate level in this sort of bulk fashion, even though we do get the fidelities to pointwise multiplicative accuracy. Okay, I have 10 minutes. For sparse Pauli channels, I'll just briefly state the results. The result is basically that you don't have to do like a full reconstruction of all the Pauli error rates. These Fourier inversion steps that convert us between Pauli error rates and Pauli fidelities, I can use a submatrix of this Fourier inversion trick to try to estimate just a smaller subset of the relevant Pauli error rates. And if I do this, I can learn the dominant error rates by using a sort of sieving technique and a divide and conquer algorithm to learn them as they, I can learn them in order as the dominant error rates in sequence, okay? And if I do this, then I get the following error guarantee. I can learn with this many samples, I can learn the log n comes from sort of searching to try to find the right and most relevant Pauli errors. I get this accuracy plus it's sort of robust to model errors. So if the channel's not really S-sparse, if there are some extra, you know, the channel can have no non-zero error rates, but I sort of truncate it and pretend that it's S-sparse, then I'm going to make a fundamental model error. And there's some, that's a typo. I should have like some coefficient here. But you get something proportional to the 2 norm of the error that you've neglected. So it's robust in that sense. And the specific scaling that we have, we can prove it's either, we can prove S to some constant power, which is reasonably small, but the scaling that I'm quoting here is modulo a conjecture, which is kind of interesting about the minimum singular value of a submatrix of a Hadamard matrix. So okay, the last thing that I want to talk about is this learning algorithm for Markov networks. So just to remind you, many of you may know what is a Markov network or a Markov field. So it's specified by a bipartite graph. So I'm going to have variable nodes and I'm going to have factor nodes. And what this means is this is a description of a factorization of this probability distribution over these random variables. So the x1, x2, x3, x4, these are going to be random choices of Paulis, okay? And depending on, so in this one I have a factor that couples 1, 2, and 3, and a factor that couples 2, 3, and 4. So that means that I can express this probability distribution in terms of 2 positive valued functions together with some partition function such that it factorizes into functions that depend only on these bits, the bits that are coupled to the factors. Okay, if I had chosen a different bipartite graph, it would lead to a different factorization. So these phi i's are called factor potentials. Some people call the log of phi the factor potential. And they're strictly positive functions. The boundary, I'll also define given a set. I'll have the boundary of some set. So if x1 is my set, because x1 touches both of these guys via these 2 factors, I'll say that the boundary of S is here, these points in red. And the closure is the union of the boundary and the bulk. And so this graph, it doesn't matter how I write it, it's only the topology that matters. If it's just bipartite, then I'm not going to bother writing the factors, I'll just use the graph, and the edges are implicitly the factors. So okay, for the rest of this talk, I'm going to assume that I know the graph structure. That is, I'm not going to try to learn which edges are non-zero. That's a different task. You can also do that in polynomial time, but I'm not going to talk about that. I'm just going to try to estimate the parameters themselves, assuming that I already know this graph. So I just want to estimate these click potentials or these factor potentials. Okay, so it's sort of obvious what we're going to do. Somebody hands you their surface code implementation on, you know, 1,000,000 qubits, right? And you're just going to sweep over things. You're going to pick a qubit and you're going to estimate the marginal error rates on that qubit and its neighbors with respect to this Markov field. And then you do it again, and you sweep over the entire Markov network, measuring everything and all of its neighbors. So if this Markov network is bounded degree, then each one of these Hilbert spaces is constant size. We can apply the estimation protocol that I went over initially. What's left to do is to round these local estimates into a consistent global estimate of a probability distribution. Okay, and so in order to do that, the Hammersley-Clifford theorem tells us that in fact it's possible to stitch together all of these local marginals into a coherent global estimate of the probability distribution. But unfortunately, the standard variant uses things that are exponentially small and so therefore exponentially hard to estimate. So we use a variant of it where we only need to know the conditional marginals conditional on the Markov shield surrounding a specific bit. And if you do that, you can write down an analytic formula for our estimator. And this is sort of key, or else we wouldn't be able to retain this multiplicative precision. So this is an analytic form for our estimator. This is an analytic form for the click potential given a specific Markov field. And if you just plug in, put a little hat on this P, you get our estimator for each of the click potentials, where here C star is just the collection of all the subfactors of each of these factors. Thank you. And so the total sample complexity, like as I said, if our estimate of this Markov field is Q, we get a one norm estimate, which is multiplicative in this sense. And the sample complexity is, it's going to be exponential in K, the degree of this Markov random field. And it's going to be like n squared log n divided by epsilon squared, where epsilon is multiplicative accuracy, together with this extra factor, which has to do with positivity. So again, we need to be able to say that each of these local marginals is never too close to zero. So I take the geometric mean of how close my estimate is and the true marginal distribution is to zero, and this somehow controls, this seems, I don't know how to get rid of this factor. Okay, so I also simulated this numerically, and this is a reconstruction of a 100 qubit noise channel that I did on my laptop, and I assume that there's nearest neighbor correlations in this device, and I can reconstruct an efficient description of the entire 100 qubit noise map using about 200 samples per factor, so 200,000 times 100 qubits, although many of those can be parallelized. And the point of this graph is to just show you that if I fix the number of samples per factor, the error does grow, but it only grows slowly, and sort of shows that this this n squared scaling can actually probably be improved a little bit to something more like n to the 3/2 if I want to bound. This is a proxy for the one norm. It's an upper bound. Root 2 times that or something is an upper bound on the one norm. And now, this may be a little bit heretical for a theorist to show experimental results at QIP. But we're doing experiments on the IBM quantum device. So this is the 16 qubit device, or one of the 16 qubit devices that IBM makes available online in the IBM Quantum Experience. And so they can do nearest neighbors between qubits in this architecture. And we thought it would be nice to characterize all of the error rates in this device. We actually wound up using a simplified version of this protocol where instead of averaging over the single qubit Pauli group, we average over the single qubit Clifford group. And what that does is it just coarse grains the errors by marginalizing each of the local bases. And so now I'm not learning all of the Pauli error rates. I'm learning, is there an error or not on this qubit, irrespective of whether it's X, Y, or Z. And so that reduces the total number of errors from 4 to the n down to 2 to the n. So it's still a large number of errors. And for 16 qubits, that's actually at the edge of tractable. And just to show you the power of this, we can reconstruct all of the error rates and their correlations on this 16 qubit device. So if I define a random variable x to be 0 if qubit xj is 0 if qubit j has no error, and it's 1 if qubit j has some Pauli error, either x or y or z, then I can define the covariance matrix to just be, the standard covariance matrix, where this is the vector of means, and the diagonal of the covariance is each of the variances of each of these error rates. And if I normalize the covariance by, I normalize the rows and columns by the standard deviations, then I get what's called the correlation matrix. So this is the Pauli correlation matrix, or the correlation matrix of all of the Pauli error rates that we have in this device. And this is sort of a coarse graining or a marginal of this is an n by n matrix for an n qubit device. Normally you would have a 2n by 2n matrix, but again, we've marginalized out the local basis choice. So it's just an n by n matrix. And you can, because of this normalization, the diagonal elements here are all 1, which means, which is represented here by a white square of unit area. The relative area of all the other things, if it's white, that shows you the relative magnitude of that correlation. If it's black, that's the signed area. So that would be an anti-correlation. So some of the errors in this device are actually anti-correlated. And so you see that the structure of the errors closely tracks the geometric locality of the qubits in this device, which is maybe not a huge surprise, but this quantitatively gives a precise and quantitative understanding of all of those correlations. And it does so in a way, it's a tensor network description at the end of the day. So this plugs directly into things like decoders, and it lets you optimally decode and things like this. I'll just wrap up. So, we have all of these beautiful tools that have been developed over the years, like gate set tomography, randomized benchmarking. And if we can project the noise into the Pauli basis, we can actually learn that Pauli noise very, very efficiently and in a useful form, in a tensor network form, if it happens to have Markov field type correlations. Once you learn that form, this Pauli correlation matrix, for example, you can use this to tailor your quantum code to the specific noise of your device, to do optimized decoding algorithms that take advantage of things like noise bias and noise correlations. You can use this to get accurate threshold information by mapping it over to StatMech models and using this Dennis et al. StatMech mapping trick to estimate thresholds in a decoder-free way, or without an explicit decoder at least. And you might even be able to optimize fault tolerance schemes to take advantage of this information. So I'm out of time, so I'll stop here, and thanks for your attention.
Hey, so you mentioned that you could deal with the probabilities of the different types of polys being different. Sometimes like Z polys are never actually applied on machines. Like they use a gate set where it's just not relevant. Does that help or does it hurt if you can only do X and Y and Z is done in software?
Well, I guess it helps because that's just one fewer error that you have to characterize, right?
Right,
If you're doing the Z's in software.
You also lose it as a tool. Like you're
Well, I think the only thing that would do here is it means that you would have to appeal. One of the assumptions that I made was that in the derivations is that the noise is gate independent. So your Z error has zero noise on it. It would violate that assumption. But that assumption is inessential. So as long as you just actively implement it, meaning you do your software implementation of Z while you're using this protocol, it doesn't matter that the error rate on that doesn't actually exist. It's zero. You can still do the protocol. And the fact that it has a different error rate than the other Paulis will not be of any material relevance because of these results showing that these methods are generally robust to gate-dependent noise.
okay. If you did it to all three, then clearly it wouldn't work though, right? If all three.
Well, if you could do all three Paulis perfectly.
Well, sometimes they're all three done in software with a Pauli frame, right?
No, well, yeah, I guess you could do that. I don't see why you couldn't. Well, I have to think about that. You want to just do it without doing it. It seems like cheating. I have to think about that.
Yeah, okay. Thank you.
Other questions?
So, okay. Am I actually audible?
I can hear you, yes.
Awesome. So back to the gate independence of the noise, and you'd said that can be relaxed, but I want to poke at that a little bit more to understand it. The results that you put up for the quantum experience sort of described the whole device, the 16-qubit device, using one plot that sort of corresponded to a single error channel.
Yeah.
But if I have if I were to have the quantum experience, loaded up on my laptop, there are lots of different gates, ranging from the idle gate, in which we sort of expect that the only thing that will be going on is T1 noise and maybe some couplings, to doing a CNOT onto the qubits, which is a big pulse that does a lot of stuff. How does your method adapt to trying to characterize those really big differences between different gates?
You don't want to characterize all 2 to the n squared Clifford gates on your n qubit device separately. right? But you can pick a few specific generators and characterize them. So the results that I showed were for trying to do the identity gate, because that's the first thing that you would do. What's the basic background noise? And then once you've characterized that, you might say, well, a natural set of gates that I might want to do would be parallel C0 gates or C phase gates between neighbors or something. And you can pick a few standard gates, or you could just do, I want to know each of my Clifford generators. There's a polynomial number of those, and you could characterize each of them. You could do each of those in sequence, and you could learn this for each of them. I mean, I don't claim to know the best way to do that, but those are all options that all take polynomial time.
Okay, let's thank Steve and thank our speakers again.